Welcome to solverfy, the place where learning becomes simple. If you're struggling with homework, assignment, or doubt in subjects, don't worry, you are in the right place.
Hello and welcome to Engineering Mechanics, Statistics and Dynamics, Chapter 11, Problem number 9. So in this question, it's going to be a little bit of a longer-winded one. We're given this diagram here to my left, and it tells us that we have two forces, P1 and P2, going down on this setup here with 30 pounds each. We have the spring here. We're given some dimensions of our apparatus here, and it asks us to determine the angle theta down here by A, at which we are at equilibrium given these forces. It also tells us that theta is 45 degrees when this spring up here is unstretched. So the first thing that we're really going to do is just calculate the force due to this spring in general. So we're going to say F sub S is equal to Kx, that K being our constant here given to us, 200 pounds per feet. But the big thing of interest here is this X. X is going to be the stretched length, how much the string stretches total. So we're going to rewrite this X as, this might be a little poor wording, and that's my mistake, but this is stretched like the total length of it stretched minus the total length of it unstretched. So our X total is going to be how much the string is stretching, excuse me. So anyway, we're going to rewrite this equation as X is equal to X sub S minus X sub U. S for stretched, U for unstretched. So what we're going to do next is write a little bit of a force diagram, really, and we're going to be thinking about the piece of information that it told us earlier with our theta being 45 degrees when it is unstretched. So if we draw a little right triangle here, we'll see that we have the angle of this theta by A is actually the same angle as this theta by D, just from, I don't know the specific mathematical justification. It's vertical angles or pairing angles. If you drew the other half of our triangle here, these two right triangles add to this together to make this equilibrium, or this equilateral right here. So this theta over here is this theta over here. Anyway, we also have 4 feet total since we have 2 feet on each side. So we have a right angle with a theta, and we have the length of a hypotenuse. So we're going to use some normal trigonometry here. So we have our theta for unstretched is 45 degrees. So we can say that the length here, right, we have the bottom half of our triangle here. This is our XU, if you can see here. And so that XU unstretched is going to be 4, the hypotenuse, times the cosine of 45 degrees. We have a cosine is adjacent over hypotenuse, and we're just going to rearrange that a little bit. So we're going to get the length of this bottom portion of our right triangle here, X sub U, and that's just going to be 4 cosine 45 degrees. And by the same token, we don't have the exact mathematics, but this is what we're going to be solving for, so we should start writing something for our stretched X. By the same token that we wrote our unstretched X, we have 4 times the cosine of whatever this theta will become when the spring stretches. So this is subject to change because we don't know what our theta is, but we were given this 45 degrees for our unstretched length. So what we can do next is continue writing that force equation. So Fs is equal to K times X, which is that 200 for K, times the two equations we have here for XU and XS. So we're going to have 4 cosine theta stretched minus 4 cosine 45 unstretched. So what I'm going to do next is just some algebra. I'm going to pull out the 4's from each. I'm going to solve cosine theta, cosine of 45. It's root 2 over 2. That's something from your unit triangle. And that's pretty much all I'm going to be doing. So we're going to bring out the 4 and have 800 times the quantity of that cosine theta minus whatever our cosine of 45 was, which is root 2 over 2. So now we're going to be getting into the more virtual work section of this problem. So I'm going to ask that you consider the positions of certain places. So we're going to have to write something that shows the position at which our spring is giving force, as well as the positions of where our pressures, our P's are going to be applied. So what we can say is we have X from the force spring. We're going to call that X. It's just an arbitrary moment in space here, is that's going to be 4 cosine theta. Just like it is over here, 4 cosine theta. So that does carry over from that logically, in terms of that's the mathematical equation. It also is for the mathematical framework. It's going to be where our position is going to be, where we're considering this force. And so again, we're going to take the differential of that, which is going to be cosine. The d of a cosine is going to be negative sine times the d theta. So we're going to have delta x sub fs. I know it's a lot. Sorry, is equal to negative 4 sine theta d theta. And a similar thought process is going to go into our pressures, our P's. We have yp is 4 sine theta. So if we're going to go back up here to our triangle, the sine is going to now be looking at this vertical component as opposed to the horizontal ones that x were. So we're going to go back down to that. Our y is going to be 4 times the sine of theta, and our differential is going to be similar now, 4 cosine theta d theta. And at this point, we can pretty much just get right into our du equation here. We have du is equal to 0, but that's going to be equal to, this is a negative fs, because the spring force is always a restorative thing, so it's going to be negative. That's important. So negative f sub s times dx minus p1 dy minus p2 dy. Right, and if we're at equilibrium, that's the point, or that's the whole point of our du equation here. It's going to be all equal to 0. So what we can do now is plug in our values for dy. This is actually dy sub p, and this is also dx sub fs, as we wrote up here. So we're going to plug in these values for dx and dy that we have here, as well as we're going to plug in our p's and that spring force equation we wrote all the way back up here. So just putting all these numbers in, it's kind of a big equation, but I'll go through it bit by bit. So we have the negative here, that's important. We have negative 800 cosine theta minus root 2 over 2. That's all standard. And then we're going to substitute that dx in right here. So we have the negative 4 sine theta d theta that we saw up here. Negative 4 sine theta d theta. And so what we're going to do next is we're just going to combine these two p's because they are the same, 30 each of them. So just 30 times 2 is 60. And the same thing goes actually for these dy's. So these are pretty much the same equation, but we just have this thing times 2, essentially. So we have negative 60 times 4 cosine theta d theta. And so at this point, it's just a little bit of algebra to get us down to where we need to, but stay with me here and we'll get there. So I'm first going to distribute my negative 800 into all of this. And then as well, we're going to distribute this negative 4 sine theta into everything here. So it's going to look a little messy. So we're going to have this negative 800 cosine theta, right? Multiply that by this negative 4 sine theta. And that'll give us 3,200 sine theta, cosine theta, or cosine theta, sine theta, it doesn't matter. And then what we need to do next is, again, look at this negative root 2 on 2. So we're going to multiply negative 800 into that. So we're going to get, 400 root 2 positive. But then this negative 4 sine theta comes in again. So we're going to have negative 1600 root 2 sine theta. And then finally, we really are just multiplying this 60 times this 4. So we're just going to have negative 240 cosine theta. So here is our equation that we're basically looking for. We have all the components we need here. I am going to simplify some of this stuff really quick, just for the sake of having less zeros and less trigonometric functions. So I have f of theta. We're just going to call this whole equation f of theta. It should be equal to 0 ideally, and that's just going to be, we're going to take out I think it's 80 from each of these terms. We're going to divide everything by 80 cosine theta. So we have 4 sine theta, that cosine theta goes away, minus 20 root 2. And sine over cosine of the same angle is going to be a tangent. So I have that there as well. Tangent of theta minus just 3, because 3 times 80 cosine theta is 240 cosine theta. All right, and so from this point here, it's really just a matter of guessing and checking. Since we do have, by the nature of these trigonometric functions, I don't know, I forgot the math word here, but they have two solutions to each of the equations, right? Sine of an angle can be is equal to one half, right? If we have sine equaling one half, sine can equal one half in two different places on your unit circle. So we're going to have two different answers for these thetas. So, and it's just going to be whichever ones are closest to 0 that you can get. So I have a little table here of thetas and the solutions f of theta. So we're a little too high at 17, a little too low at 16.5. So I settled at 16.64. It's pretty close to 0, 0.07. And the same thing goes around here. We have 36, which is too low, 35, which is too high. This one's pretty close to. It's actually the same, basically the same margin of error, but negative for 35.8. So that's also an acceptable answer. But I just brought it down by 1/10 of a 1/100th. So we have 0.058. Both of these numbers are the closest to 0. So what that means is that our angles are 16.64 and they're 35.79. Or they can be, as long as it's very close to 0. Whatever number you get that's close to 0 is going to be your solution.